Hey, this is Mr. Warden. I'm going to do a quick video key for exit ticket 17.2 for Friday in geometry. So here we have a couple of proofs aside from the other questions. So prove this. We're trying to prove ABE is isosceles. And I've indicated the reflexive property and overlapping triangles are your friend here. And you'll possibly need these theorems here. Theorem 19, which says that if two sides of a triangle are congruent, the base angles opposite them are congruent. So these two sides here are congruent, then these two angles at the bottom are congruent. And theorem 20, which says that the base angles are congruent, so basically saying the reverse, the legs opposite them are congruent. So if the base angles are congruent, then those sides are congruent. Okay, here we go. So we're going to try and prove this. We want to prove ABE, triangle ABE is isosceles. And we've been given that AD and BC are congruent. So here's AD and BC. We've been given that those are congruent. So a little hash mark, a little tick mark, I should say there. And then we've also been told that DAB and CBA are congruent. So I'll label those. So we've been told that this angle and this angle are also congruent. Okay, and we need to prove that this is isosceles. Now, in order to prove this is isosceles, what would probably be useful would be to be able to prove that these two angles EAB and EBA are congruent. Well, notice that we have two overlapping triangles that each contain those smaller angles. So we won't need addition property at all. And we have that both of those triangles share the same side. So that's where the reflexive property is going to come in. So we will be able to prove that this side is congruent to itself based on the reflexive. And I think that will lead us to the base angles, which will lead us to the opposite sides being congruent, which will lead us to isosceles. So after the givens, we can state that AB is congruent to BA, okay, by reflexive property. Okay, and once we've done that, we have enough information to say that triangle DAB is congruent to triangle CBA. DAB is congruent to triangle CBA by side angle side postulate. And once we've proven that, we can declare that angle EBA, oh my goodness, my battery is running low, and that is strange. I'm going to have to pause the video and take care of that. Okay, I'm back and I have electricity. Yay! So now we have angle EAB, as I was saying, EAB is congruent to angle EBA by Kappa-Kadika, because these angles are the small angles of these overlapping triangles, which have been proven to be congruent. Once I've proven that, I can say that EA is congruent to EB by theorem 20, which says, or sides opposite congruent base angles are congruent, okay, in a triangle, of course. That would also be true of a trapezoid, by the way. Okay, and once we've proven that, we can say that triangle ABE is isosceles because it has two congruent sides. Cool, there we've proven it. Now let's take a look at this one. Might have some overlapping stuff going on here. Here we're not proving it's isosceles. We start with that we have an isosceles triangle. And what it says is FJ is the base of an isosceles triangle. FJ is the base of an isosceles triangle. Now, the only triangle that has FJ as its base is this big one, MFJ. Okay, and we've been told that FG is congruent to JH. Let's start labeling some of this stuff. So we know that FG is congruent to JH. We know that O is the midpoint of MF and K is the midpoint of MJ. And that's going to lead us to some more stuff in a second. Okay, so givens. And I've labeled the one given that really we can label from the givens directly. But now we can also say that OF is congruent to KJ. I'm sorry, not to KJ. We can't say that. We can say OF is congruent to, so hold off. We don't need to do that yet. So first of all, we know that this is that we have a base side of an isosceles triangle. So the first thing we ought to do is actually declare that angle F and angle J are congruent. Okay. Angle J, and that's because base, okay, if, actually we can do that. We need to say this first. We need to actually say that MF and MJ are congruent. MF is congruent to MJ. We need to state this because just saying isosceles doesn't state it. You actually have to say it that they are because of definition of isosceles. Okay, and maybe we ought to say that MFJ is isosceles, okay, IFJ being the base of an isosceles. I think we need to do that. That could be argued, by the way. Okay, so we now can say, once we've said that those two sides are congruent, we can say that angle F is congruent to angle J because they are opposite to congruent sides of an isosceles triangle. Okay, and that's theorem 20. Now that we have that information, I'll label that. I'll label with yellow. Okay, so this angle is congruent to this angle. Okay. Now, we also could prove that this side, so we could prove that FH is congruent to GJ, or FH is congruent to JG. Okay, by addition, because we would be adding the same thing to two congruent pieces. Okay, now we can also, because this is an isosceles triangle, we've already said that MF and MJ are congruent. So I should actually label that too. So this is congruent to this, because we already know that because of isosceles triangle. Because we can say that, we can actually say OF and KJ are congruent. Okay, by definition of midpoint. Okay, actually really by division. Okay, since so because of definition, and definition of a midpoint. A definition of a midpoint means that we would be dividing congruent things in half and getting congruent quotients. So once we've done that, now we have enough information to prove that these two triangles are congruent. So we can prove that OF and KJ are congruent. So now we can prove that these two triangles are congruent, and that'll lead us to OH and KJ. So triangle OFH is congruent to triangle KJG by side angle side postulate. Okay. And there's the side, there's the angle, and there's the side. Side, angle, side. Okay, finally, once we've got all that, we can say OH is congruent to KG by Kappa Kataka. All right, I hope that helped.